In continuation of my lectures on quantum mechanical postulates, today I shall try to explain the postulate number 2, which gives the calculation of exact value of properties of a quantum mechanical system. This a system may have some properties which remains constant while a number of measurements is done for that property, and some other properties are also there which becomes spread in the measured values of the properties. We shall today discuss this eigenvalue equation, which will provide the exact value of the properties for a given state of this system. This eigenvalue equation A cap and psi I equal to lambda I into psi I. This is the eigenvalue equations of this property whose magnitude is lambda I. A cap is the property, A cap is the operator of the physical property. So, it is linear and Hermitian. This lambda I, the eigenvalue of the ith state of the system, and it provides the magnitude of the physical quantity. Or the state of this system. This one is the eigenfunction of the ith state of the system, and it is well behaved, quantum mechanically acceptable. Though this operator and the function may be imaginary, quantity, but this lambda I is always real, as this operator is Hermitian in nature. Whenever the eigenvalue equation for this property is satisfied, we shall get this exact value or precise value of that property for this state of this system. Whenever the eigenvalue equation is not satisfied, there will be a spread in the measured values of the property, and we remain in that case satisfied with this average value of the property. This average value of this property, how it is calculated, I shall discuss in postulate number 3 in my next lecture. Today I examine whether two properties I shall choose. One is kinetic energy and another is the total energy of 1D simple harmonic oscillator, and see whether this kinetic energy and total energy will satisfy the eigenvalue equations or not. The wave function of the system means one dimensional simple harmonic oscillator. This is psi equal to a into e to the power minus beta x square by 2, where beta equal to h cross inverse 1 root over mu k. H cross is the reduced Planck's constant and mu the reduced mass and k the force stretching constant of this system. A is normalization constant. First, I considered the kinetic energy property, whether it satisfies the eigenvalue equation for this wave function psi x. T cap is the operator of this kinetic energy. Psi x equal to operator for this kinetic energy is minus h cross square divided by 2 mu into d2 by dx square, and the function is this one, equal to minus h cross square up to mu d by dx, and it will be operated twice, d by dx and the function. And again this one equal to minus h cross square 2 mu d by dx, and whenever operating this one with differentiating with respect to x, a e to the power minus bx square by 2 into this one minus 2 beta x by 2, 2 cancels. So this minus and minus plus h cross square beta is coming here upon 2 mu d by dx, and x a e to the power minus beta x square by 2. Then again h cross square beta by 2 mu, and whenever it is the product of the two functions and of differentiating with respect to x, first x with respect to differentiation into 1, and so this function is here, and plus x remains intact, and this function is differentiated a e to the power minus beta x square by 2 into, and this minus 2 beta x by 2, and again this h cross square beta divided by twice mu, and here it is 1 minus beta x square, and the function is taken as the common, equal to h cross square beta divided by twice mu into 1 minus beta x square, and this one we can write psi x, and this is not the constant, not equal to, this value is not equal to the constant and this multiplied by this function. So this eigenvalue equation is not satisfied by this kinetic energy of this system. Beta kinetic energy varies with the value of x, means displacement of this oscillator. And next I shall try. So there will be a spread of the properties of this kinetic energy, and not we shall have the precise or fixed value of this kinetic energy for this system. Then 2, total energy operator, Hamilton operator psi x equal to minus h cross square by 2 mu d2 by dx square plus this potential energy half k x square into psi x, and this one gives already here h cross square beta by 2 mu 1 minus beta x square into psi x, plus half kx square and psi x, this one. So this h cross square beta by 2 mu and minus, whenever it is multiplied, h cross square beta square x square divided by 2 mu and psi x plus this one half kx square potential energy operator and psi x. And whenever we are taking this common psi x from this both, we get h cross square by 2 mu, and in writing this value of beta equal to h cross inverse 1 over mu k minus h cross square by 2 mu into beta square, means h cross inverse 2 into mu k and x square, here psi x common plus half k x square. So whenever resulting this 1 cross will cancel, then h cross by 2 and mu here combining this root over k by mu minus half k x square. This mu inverse 2 and h cross inverse 2 and h cross square cancels, mu cancels, then half k x square plus half k x square psi x. This two will cancel, and we are having this value half h cross root over k by mu into psi x equal to half h 1 by 2 pi root over k by mu and psi x, and this value 1 by 2 pi root over k by mu is the frequency of this oscillator, and so half h nu naught is the frequency of this operator in this ground state, and psi x. So this total energy of this one dimensional simple harmonic oscillator in the ground state is this one, and the eigenvalue equation is totally satisfied. So this one equal to E into psi x. So from these two calculations side by side, I can explain this total kinetic energy is not the kinetic energy of the system will not give this precise value. It will vary with this x and displacement, and total energy will give a precise value, and this is E, and E equal to half h nu naught, where nu naught equal to 1 by 2 pi root over k by mu. Of course, one conclusion I can also draw: whenever x is 0, means whenever the oscillator in this equilibrium position, x equal to 0, this value of this kinetic energy becomes h cross square beta by 2 mu. In this case, this value is equal to this one, and gives total energy. Whenever the oscillator is in the ground, in the equilibrium positions, means x equal to 0, the total energy and kinetic energy becomes the same. Now I shall see how the eigenvalue equation would be solved to get this expression of this eigenfunction and the value of this property, means eigenvalue, by solving this eigenvalue equations with considering some boundary conditions. An example of solving this eigenvalue equation, I take an example: a rotating system. A particle is rotating on this xy plane along this z axis. The phi is changing while the particle is rotating, and range of this phi is 0 to 2 pi. Then we have considered the z component of angular momentum property of this system. Lz cap into psi phi equal to Lz psi phi. Here the wave function is a function of azimuthal angle of phi. This Lz cap, already I have discussed this Lz cap equal to minus IH cross dy d phi in polar coordinates. So minus IH cross dy d phi psi x equal to Lz psi phi. And this psi phi is coming here, d psi phi divided by psi phi equal to minus Lz divided by IH cross into d phi. This minus 1 you can write, this minus 1 you can write this I square, and here this I square and this I cancels, one I remains and it plus I Lz by H cross d phi. We can write this one I m d phi, where m is equal to Lz by H cross. So Lz becomes m into H cross. This is the eigenvalue of this equation. Then whenever we are considering the eigenfunction, then ln psi phi equal to I, whenever integrating this one, integrating this equation, ln psi phi equal to Im phi plus ln A. Ln A is some integration constant. So this value psi phi equal to A into e to the power Im phi. A is normalization constant, and the normalization constant could be evaluated by putting this normalization condition. This value of this range of this phi is 0 to 2 pi for one complete rotation. So psi phi, and it is the imaginary function, so psi phi into psi star phi, complex conjugate of this one, into d phi equal to 1, or a square e to the power Im phi into e to the power minus Im phi, it is the complex conjugate of this one, into d phi equal to 1. These two products equal to 1, so it is d phi when integrated, it will give a square 2 pi equal to 1, or a equal to 1 by root over 2 pi. This is the value of this normalization constant. So the normalized wave function for this system is 1 by root over 2 pi e to the power Im phi. Now our next task is to find the value of m, or you can say evaluation of m. Psi phi, you can see this same position is coming back for this particle after covering this 2 pi. So the psi phi will be equal to psi phi plus 2 pi. 2 pi is the maximum, is the azimuthal angle covered for one complete rotation. So this could be written as 1 by root over 2 pi. This is the condition imposed to find out the value of a. 1 by root over 2 pi e to the power Im phi into e to the power 2 pi Im. So whenever this one and this one getting cancelled, and so e to the power 2 pi Im equal to 1. Converting this one into sine and cosine, cosine 2 pi m plus I sine 2 pi m equal to 1. And this equation is satisfied only when this m equal to 0, plus minus 1, plus minus 2, plus minus 3, and etc. When m equal to 0, this value equal to cos 0 equal to 1, and this value 0. And when 1 plus 1 minus 1 plus 1 plus 2 minus 2, in every case this equation is fully satisfied. So we come to the conclusion that the eigenfunction of this system psi equal to 1 by root over 2 pi e to the power Im phi, and eigenvalue this Lz, z component of angular momentum, equal to mh cross, where m, value of m equal to 0, plus minus 1, plus minus 2, plus minus 3. I can suggest for the students to see this energy eigenvalue equation for the system H cap psi phi equal to E psi phi. Whenever you solve this equation, you will find the expressions of this psi phi and also the energy value of this system H cap. Already discussed Hamiltonian operator for this energy property equal to minus h cross square divided by twice I is the moment of inertia of the system, d2 by d phi square. This is all about the postulate number 2. I have given one also example how to wave eigenvalue equation and could be solved taking some boundary conditions, and we can get the expressions of this eigenfunction and the exact value of this exact value of this property given by this eigenvalue. So this is all about for this lecture number 7, and again I thanks to you all who are watching this video. If you like, then please subscribe and share.